नमस्कार, मैं आनंद कुमार खत्री। आज के हमारे लेक्चर का विषय है एटमॉस्फेयर, पार्ट 4। एटमॉस्फेयर एंड मेसोस्फीयर. The stratosphere is located above the troposphere and extends up to about 50 kilometers above the tropopause and the isothermal layer. In the lower stratosphere, temperature increases with height. Temperatures as high as 0 degree centigrade and observed near the top of the stratosphere. The observed increase of temperature with height in the stratosphere results in strong thermodynamic stability with little turbulence and vertical mixing. The warm temperature and very dry air results in an almost cloud-free volume. The infrequent clouds that do occur are called nacreous or mother of pearl clouds because of their striking iridescence, and they appear to be composed of both ice and supercooled water. These clouds forms up of height of 30 kilometers. The pattern of temperature increases with the height in the stratosphere is the result of solar heating as ultraviolet radiation in the wavelength range of with height in the stratosphere in the result of solar heating as ultraviolet radiation in the wavelength range of 0.200 to 0.242 micrometer dissociates diatomic oxygen. The resultant attachment of single oxygen atoms to O2 produce O3. The natural stratospheric ozone is produced mainly in the tropical and middle latitudes. A region of nearly complete ozone depletion which have occurred in the Antarctic during the spring are associated with nacreous clouds. Chlorofluorocarbons, CFC, and other pollutants from human activities. These regions are more commonly known as ozone holes. Ozone is also transported downward into the troposphere vicinity of the polar front. The stratopause caps the top of stratosphere, separating it from the mesosphere near 40 to 50 km an altitude and a pressure of 1 millibar, equal to the 0.75 mm of mercury at 0 degree centigrade. In the mesosphere, temperature again decreases with increasing altitude. Unlike the situation in the stratosphere, vertical air current in the mesospheres are not strongly inhibited. Ice crystals clouds called noctilucent clouds occasionally form in the upper mesosphere. Above the mesopause, a region occurring at altitude near 85 to 90 kilometer, temperature again increases with height in a layer called the thermosphere. Temperature in the thermosphere range from near 500 Kelvin during periods of low sunspot activity to 2000 Kelvin when the sun is active. The thermopause defined as the level of transition to a more or less isothermal temperature profile at the top of the thermosphere occurs at height of around 250 km during quiet sun period and also almost 500 km when the sun is active. Above 500 km, molecular collisions are infrequent enough that temperature is difficult to define. The portion of the thermosphere where charged particles, ions, are abundant is called ionosphere, and these ions results from the removal of electrons from atmospheric gases by solar ultraviolet radiation extending from about 80 kilometers to 300 kilometers in altitude. The ionosphere is an electrically conducting region capable of reflecting radio signals back to the Earth. Maximum ion density, a condition that makes for efficient radio transmissions, occurs within two sublayers, the lower E region, which exists from 90 to 120 kilometers in altitude, and the F region, which exists from 150 to 300 km in altitude. The F region has two maxima during daylight hours called F1 and F2. Both the F1 and F2 regions possesses high ion density and are strongly influenced by both solar activity and the time of day. Of these, the F2 region is the more variable of the two and may reach an ion density as high as 106 electrons per cubic centimeter. Shortwave radiation transmitter capable of reaching around the world take advantage of the ability of layers in the ionosphere to reflect certain wavelengths of electromagnetic radiation. In addition, electrical discharge from the tops of thunderstorms into the ionosphere called transient luminous events have been observed. Magnetosphere and exosphere. Above approximately 500 km, the motion of ions is strongly constrained by the presence of Earth's magnetic field. This region of Earth's atmosphere, called the magnetosphere, is compressed by the solar wind on the daylight side of the planet and stretch outward in a long tail in the night side. The colorful auroral displays often seen in the polar latitudes are associated with bursts of high energy particles generated by the sun. When these particles are influenced by the magnetosphere, some are subsequently injected into the lower ionosphere. This is the Von Allen radiation belts, which showing the different layers of radiation. The layer above 500 km is referred to as the exosphere, a region in which at least half of the upward moving molecules do not collide with one another. In contrast, these molecules follow long plastic trajectories and may exit the atmosphere completely if their escape velocity are high enough. The loss rate of molecules through the exosphere is critical in determining whether Earth or any other planetary body retains an atmosphere. Horizontal structure of the atmosphere. Distributions of heat from the sun. The primary driving force for the horizontal structures of the Earth's atmosphere is the amount and distribution of solar radiation that comes in contact with the planet. Earth's orbit around the sun is an ellipse with a perihelion in early January and an aphelion of 15.26 million kilometers in early July. As a result of Earth's elliptical orbit, the time between the autumnal equinox and the following vernal equinox is almost 1 week shorter than the remainder of the year in the Northern Hemisphere. This results in a shorter astronomical winter in the Northern Hemisphere than in the Southern Hemisphere. Earth rotates once every 24 hours around on axis that is tilted at an angle of 23 degree 30 minutes with respect to the plane of its orbit around the sun. As a result of this tilt during the summer season of either the northern or the southern hemisphere, the sun's rays are more direct at a given latitude than they are during the winter seasons. Poleward of latitude 66 degree 30 minutes north and 66 degree 30 minutes south, the tilt of the planet is such that for at least one complete day and as long as 6 months, the sun is above the horizon during the summer season and below the horizon during the winter. As a result of this asymmetric distribution of solar heating during the winter season, the troposphere in the high latitude becomes very cold. In contrast, during the summer at high latitudes, the troposphere warms significantly as a result of the long hours of the daylight. However, owing to the oblique angle of the sunlight near the poles, the temperature there remains relatively cool compared with the middle latitude. Equatorwards of latitude 30 degree north and 30 degree south or so, substantial radiant heating from the sun occurs during both winter and summer season. The tropical troposphere therefore has comparatively little variation in temperature during the year. Convection, circulation, and deflection of air. The region of greatest solar heating at the surface in the humid tropics corresponds to the areas of deep cumulonimbus convection. Cumulonimbus clouds routinely form in the tropics where rising parcels of air are warmer than the surrounding ambient atmosphere. They transport water vapor, sensible heat, and Earth's rotational momentum to the upper portion of the troposphere. As a result of the vigorous convective mixing of the atmosphere, the tropopause in the lower latitudes is often very high, located some 70 to 18 kilometers above the surface. Since motion upward into the stratosphere is inhibited by very stable thermal layering, the air transported upward by convection diverges towards the poles in the upper troposphere. As the diverted air in the troposphere moves towards the poles, it tends to retain the angular momentum of the near equatorial region, which is large as a result of Earth's rotation. As a result, the poleward moving air is deflected towards the right in the Northern Hemisphere and towards the left in the Southern Hemisphere. Upon reaching around 30 degree of latitude poleward of its region of origin, the upper level air is traveling primarily towards the pole and is tending towards the east. Since motion upward is constrained by the stratosphere, the slowly cooling air must descend. The comparisonal warming with that occurs as the air descends creates vast regions of subtropical high pressure. These regions are centered over the ocean and are characterized by strong thermodynamic stability. The sparse precipitations in these regions as result the stability and subsidence is associated with such great arid region of the world as the Sahara. Alkama, Kalahari, and Sonoran Desert. The accumulation of air as a result of the convergence in the upper troposphere cause deep high pressure systems known as subtropical ridges to form in these regions. Locally, these ridges are given such names as the Bermuda Height, the Azores Heights, and the North Pacific High. This is the sun dune. This large area of sand dunes in the southern Algeria is located within a vast region of the subtropical high pressure. The descending air referred to above, upon reaching the lower troposphere, is forced to diverge by the presence of Earth's surface. Some air moves poleward, while the remainder moves equatowards. In either direction, the air is deflected to the right in the Northern Hemisphere and to the left in the Southern Hemisphere. Deflection occurs because, in accordance with Newton's first law of motion, a parcel moving in a certain direction will retain the same motion unless acted on by an exterior force. With respect to a rotating Earth, a moving parcel conserving its momentum will appear to be deflected with respect to it to fixed points on the rotating Earth, as seen from a fixed point in space, such as a parcel would be moving in a straight line. This apparent force on the motion of a fluid, in case of air, is called the Coriolis effect. As a result of the Coriolis effect, air tends to rotate counterclockwise around large-scale low-pressure system and clockwise ground large-scale high-pressure system in the northern hemisphere. In the southern hemisphere, the flow direction is reversed. This is the Coriolis force, which showing the direction, the effect of the earth of the Coriolis force. In the equatowards moving flow, this deflection results in northwest winds north of 0 degree latitude and southeast winds south of that latitude. These low level winds have been called the trade winds since 17th century. Sailing vessels used them to travel to the Americas. The convergence region of the lower level northwest and southwest trade winds is called the Intertropical Convergence Zone (ITCZ). The ITCZ corresponds to the equatorial trough and is the mechanism that helps generate the deep cumulonimbus clouds through convection. Cumulonimbus clouds are the main conduit transporting tropical heating into the upper troposphere. The circulation pattern described above ascent in the equatorial trough, poleward movement in the upper troposphere, descent in the subtropical ridges, and equatorwards movement in the trade wind is in effect a direct heat engine which meteorologists call the Hadley cell. The persistent circulation mechanism transports heat from the latitude of greatest solar insolation to the latitudes of the subtropical ridges. The geographic location of the Hadley circulation moves north and south with the season. However, the equatorial trough lags behind for about 2 months owing to the thermal inertia of Earth's surface. For a given location of Earth's surface, the highest daily temperatures are achieved just after the periods of greatest insolation, since time is required to heat the ocean surface water and the soil. Thanks.